Right, ladies and gents, this is lesson 3 of the weather and climate module, and this is the tricellular model, the model of atmospheric circulation, whatever you want to call it. And I teach this in class by drawing it from scratch. So I'm going to try to do that in front of your very eyes. Okay, grab yourselves a piece of paper. You don't have to be able to draw this in the exam at all, but actually if you are able to, and I honestly think that once you've unpicked it and done it from scratch, it's not that tricky. If you are able to draw it, it gives you quite a few clues and it's quite a helpful diagram. Okay, I'm going to start off with a flat Earth, just because that's easier. So that's going to be my equator. That will be my South Pole. That will be my North Pole. Okay, so the equator is at, oh gosh, 0 degrees, 90 degrees, 90 degrees either way. And it's nice and easy because you go in 30-degree increments. I'm really sorry about the quality of this, but I think it's clear enough to get the idea. Now the significance of the latitude will become clearer later. I flatten the Earth, which is normally how the tricellular model is drawn to begin with. We can work our way up to a sphere, all right? Don't worry about that. So let's change the colour. You want a warm colour, a red, an orange, a pink, something like that. It's hot at the equator. We established that in the last video. Hot air rises. If hot air didn't rise, hot air balloons would be rather boring, wouldn't they? Okay, hot air rises. Grab yourself a cold colour, usually a blue. It's cold at the poles and cold air sinks. Yeah? Don't really have to remember too much there. And then I'm going to go to a neutral colour. I'll go to a black. In a convection cell, which we talked about last video, the arrows chase each other. So we can therefore add the rest of this convection cell, because we know it's hot at the equator and we know hot air rises, and we know that the arrows must chase each other. Hey presto, one of the cells is drawn. Hurrah! It's cold at the poles, cold air, oops, cold air sinks, and the arrows chase each other. Hey presto, you've drawn 2 of the cells. Now the middle cell, the best way I've got to remember it is not perfect, but it copies its neighbour on either side. So it does exactly what the next door arrow does on either side. And then the arrows chase each other. And hey presto, ladies and gents, without really working that hard, you have drawn the tricellular model. The 2 either side of the equator are called the Hadley cells. The middle ones are called feral cells. And the 2 at the poles are called the polar cells. Shock, horror. Okay, but why do I think it's worth being able to draw this? It explains so much about planet Earth, and I'll go back into my PowerPoint and prove this to you in a minute. But do you remember from the first lesson I banged on about pressure, and I said if the air is rising, we call that low pressure, and if you've got low pressure, you get cloud, you get rain, you get wind. Well, here, here, and here are low pressure areas. Let's think about the kind of plants you find at the rainforest. I've given you the answer. The kind of plants you find at the equator, you get rainforest. That would suggest it rains a lot, and it's because of this. We live nearly at this point. We have trees, we have forests, we have plants that need a lot of water. That's because we live in a low pressure area. New Zealand is here. Whereas where we have the arrows sinking, high pressure means no cloud, no precipitation, no wind. I don't know if you've ever noticed, but the world's deserts are always about 30 degrees north and south of the equator. because they are at this point on the model. The poles are classified as cold deserts. And immediately your brain goes, no, I know there's snow at the poles, so that doesn't make sense. But actually, it's just because there is snow, high pressure areas can have precipitation, just not very much of it at all. And the precipitation that falls there just stays there. So over thousands of years, millennia, you are going to get huge amounts of snow that turns itself into ice. So practice that a couple of times. But let's go back. That's what a finished, completed version looks like. But hopefully, once you can get your head around the basics, this then doesn't look quite so scary. Look, equator, 30, 60, 90. Hot air rises and the arrows chase each other. Okay, so that's quite good. Now this PowerPoint is in Office 365. It's called Climate Intro. You've got access to it. If you've lost your link, then just email me and I'll resend it to you. And that will enable you to watch all of the embedded YouTubes, which will help. That, have I got another one? And that, yes, are the spherical versions, which look terrifying to begin with. But look, actually, if you take a deep breath, it's hot at the equator, hot air rises, the arrows chase each other. It's cold at the poles, cold air sinks, the arrows chase each other, and the middle cell copies its neighbour on either side. It is exactly the same principle as the one that we drew. It just looks terrifying. Here's a map of the world, which proves to you, look, so the equator is about here. Oh look, what do you find near the equator? You find rainforest. What do you find about 30 degrees north and 30 degrees south? You find deserts. And then about 60 degrees north and south, you find forests. And then at the poles, you find your cold deserts. That model explains the biomes of the planet. It explains the climates of the planet. It explains an awful lot. So it is definitely worth trying to spend a bit of time. And as I said, you've got a couple of embedded YouTubes. This animation here is brilliant. I highly, highly recommend it. But it's quite temperamental. If you've got Microsoft Edge, it will probably not open. Sometimes it will open in Chrome. It most likes Internet Explorer and Safari. So yeah, you might just have to play around with your browser in order to get that to work, but it is excellent. And that brings us to a nice little pause point, a little checkpoint for you to kind of go, right, can I do this? Is this possible? Whatever. Obviously, I'm not going to stay on this for very long. You can pause and do whatever you want to. Okay. Then we've got a few what I call complicating factors. If you're already thinking that this model is horrible, apologies, it does get a little bit more complicated. I now need to talk to you about this, the ITCZ, and I need to talk to you about these arrows going in funny directions here. Okay, when we drew our basic version, where the hot air was rising, I labelled as the equator. Now, for part of the year, that is true, but it isn't true all year round. So in fact, really, the middle bit should not be labelled equator. It should be labelled ITCZ. That stands for Intertropical Convergence Zone. Intertropical because it moves between the tropics. Convergence, again, go back to tectonics. What happens at a convergent plate margin is that the plates are moving towards each other. If we look here, look, the wind is moving towards each other. It moves, intertropical, the wind is coming towards each other, convergence zone. That's really the name that we should give to the middle of our model where the hot air rises and the Hadley cells meet. Okay. Why does it move? Well, that brings us to the delight and joy that are the solstices and the equinoxes. And again, watch the embedded YouTube because it's brilliant. The narrator is a little bit on the patronising side, I'll be honest with you, but it is a fantastic video to get your head around this. So what I need you to focus on, look, is the daylight and the darkness. Okay, the daylight and the darkness. The Earth is tilted on its axis at 23.5 degrees. Okay, now I'm going to talk about this one because I'm making this video in December as the days are getting shorter and shorter. It's getting colder and colder. So for me right now, this one has the most relevance. Notice that the northern hemisphere is tilted away from the sun. That means that the northern hemisphere spends more time in darkness than it does in daylight. So we get shorter and shorter days. The worst it gets is on the 21st or the 22nd of December. That will be the shortest day in the UK. And then the days will start getting longer again. Now, for us in weather and climate, the length of day is not actually that important. We're interested in the heat. It always comes back to the heat. Well, if you're tilted away from the sun, then actually you're going to be receiving less heat, aren't you? So that's why we go into our winter here. Whereas 6 months later, in June, notice now that the northern hemisphere is tilted towards the sun. This is the beginning of our summer. This is our longest day, and it's all because now we are in a completely different position. Here and here, equinox is from the Latin for equal night. Here, pretty much everywhere on Earth is receiving the same amount of daylight and darkness, which is why equal night, equinox. And therefore, in September and March, that would be spring and autumn for the UK. We're between the seasons, if you like. Okay, and what that means is that where the sun is directly overhead shifts. It moves into the northern hemisphere in June. It moves into the southern hemisphere in December. The sun moves between the tropics, and I've got a few diagrams to try and help you. If we look at this in cross-section, so let's start with situation normal, which is the one in the middle. In the equinoxes, equal nights, notice that the sun is overhead the equator. So the hot bit where the two Hadley cells meet is overhead the equator, because where it's hottest is always going to be where the sun is. That makes sense, doesn't it? So the hot air rises and you get your whole model. That was the version that we drew first of all. But look, in June, the sun is shining over the northern hemisphere. And therefore, because the sun has changed position in our sky, the hot, rainy bit moves north. Whereas in December, the sun is now over the Tropic of Capricorn in the southern hemisphere, and the whole thing has shifted south. So this bit in the middle moves north and south with the seasons. This animation, again, it's a bit temperamental. You might need to open it in Safari or Internet Explorer, but it is an animation of how this ITCZ, the hot bit where it's rainy and the two Hadley cells meet, how it moves over the course of the year. And you can add on colours for precipitation, you can add on all sorts of things. It will really help you to understand. Okay, so first complicating factor. The bit in the middle, really we need to start calling it the ITCZ. Intertropical, because it moves north and south with the seasons. It moves between the tropics, the Tropic of Cancer and the Tropic of Capricorn. Convergence, because it's where the winds are moving towards each other. Now that might take you a bit of time. Remember to use the animation, use the videos I've given you to try and help. The other thing that I tend to do is I get a world map and I draw suns on it, which changes the laws of physics completely, but works for me. So in June, your sun would be directly overhead here, the Tropic of Cancer. And then in September, it would be over the equator. And then in December, it would be down here. And in March, it would be up here. So every 3 months, the sun is overhead a different one of these lines. Between that, of course, it's travelling between them. Intertropical. It moves between the tropics. Now, the Coriolis effect. There is an easy version and a complicated version. The easy version is just to say that the winds, in reality, do not go in a straight line. If we look at this model, look, these arrows would suggest that things go in a perfectly straight line from north to south or south to north. In reality, that is not true. These arrows are a map view or a bird's eye view. We're looking from above, but they are these arrows. It's just that when you're drawing in cross-section, unless you draw in 3D, which is very hard, you can't show that. So this wind here, which is trying to travel from the south to the north, doesn't actually go in a straight line. It goes in a diagonal line. At the very simplest level, all you would need to be able to say is the winds do not go in a straight line because of the Coriolis effect. That'll do you, okay? If you want to know why, if you have the sort of brain that's like, no, I've got to get my head around this. The Earth is a sphere. The equator is the fattest bit. As the Earth rotates then, the equator is travelling at about, I think it's 1,600 kilometres an hour, 1,400 or 1,600 kilometres an hour. It's very fast. If you were stood right on the North Pole, you wouldn't really move at all. You would just rotate on the spot. So there is a speed difference between the pole and the equator. And because of that speed difference, things actually can't travel in a straight line. They get deflected. So this diagram just shows you what direction things get deflected in. Do you have to remember all of that information? No. All we're saying is that actually the wind cannot, in truth, go in a straight line. It gets deflected. Now I've included 3 videos and an animation. If you decide that that's way too complicated, fine. Just come back to this. The Coriolis effect means that winds cannot actually travel in straight lines. They are deflected. If you get it, fantastic, good for you, congratulations. Don't worry. So that brings us to our second pause point, and quite enough for one video.